a little way into the lecture at this point for the benefit of those following us at home. So the top one is branch, the bottom one is staff. We're only keeping one redundant or shared column, and that's branch number. And it is a foreign key in the staff relation, so we could have duplicated all the branch information in the staff. So instead of saying that John White is in branch B005, we could have said, well, the street address is 22 Deer Road, and the city is London, and the postcode is SW14EH, but that would have contained a lot of redundant information, and if we updated that information in the branch and then update it in the staff, well, we would have inconsistent data. So this idea of only sharing foreign keys is an important one because it reduces the amount of redundant data that we store, and that in turn reduces inconsistency in the database. Now, obviously, if we update the branch number for B005 and change it to B0010, we're going to have to ensure that it gets updated in all other places as well. So it doesn't eliminate the chance of inconsistency, but it reduces it. Okay, I'm going to let you look at this slide on your own because it's just basically giving some examples of possible attribute domains. I guess the one thing I should mention is that the set of domains in relational databases can be anything you want. So it's much richer than what you're used to with programming languages. And a very common one that most vendors provide is some kind of date domain and some kind of time domain, because those are two important pieces of information that we often want to store with entities. And then this is a table that you should make sure you familiarize yourself with, because you'll definitely hear alternative terminology, and they may well be used in different people in different roles will use different terminology. So the academician is going to use, so we'll say the professor, and again, they said they had fixed the ink, but they hadn't. So I'm stuck. So I'm just going to say prof or professor. And then the user is most likely to use this terminology if you are talking to a user. And your database vendor or physical implementer who's dealing with the physical implementation is most likely to use this terminology. So roughly speaking, a relation is something that a user will call a table, and that someone at Oracle or Microsoft might well call a file. So we typically use a file to store a relation. A user will call a tuple a row, and typically a vendor will call it a record. And finally, the professor will say attribute, the user will say column, the vendor will say it's a field in the record. Most of you are probably most familiar with the vendor terminology because taking 140 and 302, we tend to talk about files, records, and fields. And that's because in those courses, we've been more focused on a file-oriented storage mechanism. In this course, we're much more going to be talking about relations or tables, tuples or rows, attributes or columns. So we're going, and I will often use those terms interchangeably. So you need to know when I talk about them, they're synonyms. So questions about that? They said this is an important table that you need to familiarize yourself with. Okay, now we descend into some of the mathematics, and which is why 311 is a prerequisite for this course. So there is a mathematical definition for a relation, and everything kind of goes from that definition. So the idea is that you have different domains. In this case, D1 and D2 are two domains. And in this case, D1 is restricted to two values, 2 and 4, and D2 is restricted to three values, 1, 3, and 5. The universe of tuples that can be created from these two domains is their Cartesian product. You'll also hear me call it the cross product. So D1 looks like a multiplication sign, D2. It's the set of all ordered pairs that you can get by enumerating all possible pairs where elements of D1 are the first element in the pair and D2 are the second element. So right here, you see our potential universe from which our tuples may be drawn. So each of those 6 pairs is a potential tuple. And any subset of that Cartesian product is a relation. Now, there are multiple ways to specify that relation. In practice, the way we do it is by simply enumerating the tuples, which is the way we've done it in Roman numeral 3. We simply have enumerated some subset of the possible tuples. That's what we do in practice. But theoretically, there's other ways to specify the pairs that are in the relation, and that would be through some mathematical statement. So in part 4, I've given you 2 examples. I could say that my relation is the set of all tuples such that y, or such that the element chosen from domain 2 is equal to 1. So that gives us 2 pairs because there's 2 values in D1, 2 and 4, and therefore that gives us the pairs 2, 1 and 4, 1. Okay, a second way to, another mathematical statement we could use is to say it's the set of all tuples such that the element from D1 is twice the value of the element from D2. Well, there's only one such pair that can satisfy that mathematical statement, and it's the pair 2, 1. So again, in practice we enumerate, but in theory we can have concise mathematical descriptions of our pairs. Okay? In fact, a query, when we perform a query on a database, such as saying that we want all staff from branch B005, we actually are making a mathematical statement about the relation we want to see. So in fact, while the tuples in our relation are enumerated, every query from a user is actually a mathematical statement of the tuples we wish to see. So users are actually dealing with part 4, whereas the database administrator is dealing with part 3. Okay? It's an important point. We good with that? Okay. So I'm not going to go through, I'll let you, this belabor it. Obviously, you can scale up to 3 sets, and you can generalize then up to an arbitrary number of domains. and the potential universe is represented with this Greek character pi for we're doing a cross product of all of those domains, and then each of the domains represents an attribute. So D1 is an attribute, D2 is an attribute, Dn is an attribute. And then you will, so we call a relation is a concrete, kind of a concrete manifestation of something. We talk about a schema as being a named relation that is defined by a set of attribute and domain name pairs. So that's the DDL description of it. Okay, so when we create a relation, we give it a name and we give it a set of attribute domain pairs, and then we say that a relational database schema is a set of these relation schemas. A schema, though, is different from a relation. A schema is a more abstract or meta concept. It's what the DDL is basically being specified by the DDL. The relation itself is more a concrete than set of tuples. When E.F. Codd defined his relational model, he attached some requirements to them. And they're not all quite lining up with what you see in 311 or Math 300. So most of them are fairly straightforward. So relation names are distinct from each other. They're unique. The next one is actually a fairly big limitation, although it's straightforward, which is each cell of a relation contains exactly one single value. It may not contain multiple values, such as multiple phone numbers. Okay? That actually is a bit of a constraint. If I want to say that, for example, you could be taking anywhere from 3 to 6 courses, I can't have an attribute called courses that has anywhere from 3 to 6 values. It would be allowed to have only a single value like CS465. We'll talk about ways to handle that restriction in other lectures, but that's a pretty big restriction. Each attribute has a distinct or unique name within a relation. The same name can be used in 2 separate relations. So back here, branch number appeared in both of our 2 relations. So it's okay for it to be reused in another relation, but within the same relation, the attribute names must be unique, which is just common sense. Okay, the values of an attribute are all from the same domain. This is another fairly strict limitation with relational databases. You can't say, for example, that a label will be either a text label or a JPEG file. It must be one or the other. Either you say labels are text labels or you say that they're JPEG files, but you can't say that they're one or the other. And this is one reason why there's been a search for other types of databases to represent data, because with social media, there are attributes where you actually would like them to be drawn from multiple domains. And the relational model does not handle that. So this is a pretty, 2 and 4 are rather severe restrictions on this model. Each tuple is distinct, so there are no duplicate tuples. Again, that's kind of a common sense thing. If you have 2 duplicate tuples and I need to update one you have no idea which one should be updated because they appear identical. So at least one attribute must differ between each pair of tuples. And finally, the order of the attributes has no significance. It doesn't matter in which order the columns are placed in the relation, which is different than the definition of a relation that you learned in CS 311, where the order of the columns did matter. Here they have no significance. Okay? Also, the order of the tuples theoretically has no significance. They may be arranged, the rows may be arranged in any order, but in fact, the order can critically affect query optimization, as you learned in 140 and 302. What do we normally do to ensure that we can efficiently retrieve data? What do we do to it? Index it, okay? So typically, and how do we index it, I guess? I'm not sure, someone over here said it, but I didn't. Was it you, Annika, or no, someone else? When we index it, what are we doing to the data? Pardon? Mapping it, okay. Sorting it, that's what I was looking for. We sort it according to some attribute. So in practice, the order makes a big difference in terms of efficiency. But in theory, there's no two instances of a relation which have the same set of tuples but which are in different orders. They're identical. Same thing with the attributes. I give you two relations and the columns are in different orders. They are the same relation. Okay. So now we move into keys, which we talked about last time. Remember, a key simply uniquely identifies an entity. But the relational model has a number of definitions for these keys. So they start with a superkey, which is any set of attributes that uniquely identify a tuple. Based on what I just said in the last 2 minutes, what is a guaranteed superkey for any relation? Guaranteed. The entire set of attributes. Because I said that each tuple is distinct. So it must be the case that a superkey is the set of all attributes for that relation. Now, we would like to do better than that because that's an awfully big key. So we move from there to a candidate key, which is what we call an irreducible key, or the smallest possible superkey. So it's a superkey such that no proper subset is a superkey, meaning if we were to remove any attribute from this set, it would no longer be a superkey. Okay, so the means that it has an irreducibility property associated with it. It doesn't mean that it is the smallest possible key. So if we go here, let's just pretend for a moment that the street and city by themselves are enough to uniquely identify a branch. Okay? Then street and city would represent one candidate key. Okay? If we removed either city or street, we would no longer have a candidate key. You can easily see that by looking at city, because there's a duplicate in city, right? Everyone see the duplicate? Street is not duplicated. And honestly, there's probably a very good chance that street address alone would uniquely identify a branch, but not an absolute guarantee. Main Street is a pretty common designation for a street, so you could end up with two branches, both on Main Street and unluckily with the same number. So we say that street and city, that the pair is a candidate key. Obviously, branch number is specifically designed to be a candidate key. Anyone else spot a potential candidate key in there for a branch? There's another one possibly lurking in there. Okay. Postcode, very good. So it very, very well be the case that we have only one branch per postcode. Okay? I think that the U.S. Postal Service is roughly aligned on that model, that there's typically one station per postcode, although it's not quite unique. Okay, so there could potentially be 3 candidate keys in there. Now you'll notice that among those candidate keys, the branch number is the most compact. But we have 3 different ones, and despite the fact that street and city combined are fairly verbose, there's still a candidate key. Now, from those candidate keys, we select one of them to be the primary key. Okay, so even though there may be multiple candidates, we select just one. Normally, it's an artificial key that we have specifically created for that relation, like branch number, lease number, confirmation number, because it guarantees uniqueness and because it's compact. Sometimes, if we have a very good natural key, we wouldn't add an artificial key, because an artificial key obviously takes up a little more space and it's not as intuitive for a user to deal with. Okay, it's much easier to remember that the name of some branch is the Golden Branch rather than branch B005. But in practice, we usually have to add an artificial key and designate it as the primary keys. Any candidate key not selected to be the primary key is called an alternate key. So coming back to this particular example, street, city would be an alternate key, postcode might be an alternate key. Okay, so questions about this terminology? Oops. Okay, and then a foreign key, as I said last time, it's an attribute or set of attributes within one relation that matches a candidate key in some other relation. It could possibly be the same relation. Typically, the foreign key is a primary key in another relation, but it doesn't have to be. Okay. So if we go back here, the branch number, so here in the staff relation, the branch number is a foreign key. Okay, if you look, can someone tell me why it can't be a primary key in staff? Why can't it be a primary key within the staff relation? Very good, because multiple people work in the same branch, and therefore that value isn't unique. If you look here, B0, we see that John White and Julie Lee both work at branch 5, and there's 3 people that work at branch 3. So it's not a unique key, or it does not uniquely identify tuples in the staff one. Now, this also raises, so at any rate, those are foreign keys. Foreign keys are used, though, to establish relationships between relations, and also they allow us to easily combine them so we don't have to redundantly store information. So if I want to find out which city John White is working in, I can simply, in effect, follow his foreign key, B005, use it as a entry point into the branch relation and find out that he works in the City of London. So foreign keys are going to allow us to, in some sense, glue together or join relations together. They also provide, another way to think of it is they provide pathways between relations. So let's now consider, just take a moment and consider this schema, actually set up. So this is a database schema, the whole thing. Now, I did not give actually the domain for each of my attributes. So this is actually an abbreviated schema. For it to be a full-on schema, with each attribute, I would have had to list its domain value. But we're going to be using this one a fair amount over the next couple weeks. So we are running a hotel chain. So we have a number of hotels which we store in our hotel relation. And then we have a number of rooms that have a type like double, single, suite, executive, and a price we charge for each night. We have bookings for rooms, and we have a relation of our guests. Okay. So if you look at this, it's fairly obvious, or should be fairly obvious, what we are using as primary keys for hotel and guest. Okay, is hotel number and guest number. Let's see if I have, nope I don't. However, let's look at that room relation. Is room number by itself enough to uniquely identify a room? Why not?
There could be the same room number at different hotels.
Very good. What about, so then since we can't get it by room number, will hotel number by itself work? Also not, because presumably, unless we're running a pretty fancy hotel, we have multiple rooms in each hotel. Okay, is type going to work? No, because obviously we may have multiple doubles, we may have multiple suites, and obviously price isn't going to do it for us either. So what do you think might be, so we can't do it from a single attribute. There is no attribute here that by itself gives us a uniquely identifies it. So is there a pair? Yes. Which? Hotel number and room number together should do the trick. Okay. If we duplicate the room number within a hotel, we should expect our guests to be pretty confused. Okay. So it is quite likely that we have that pair is going to give us a primary key. In fact, there is really no other likely candidate key here. Any other possible combination is likely to yield duplicates. Now let's take a look at booking. Okay, and I can pretty much tell you right away that no single attribute is going to work either. Okay, certainly we hope to have multiple bookings for each hotel. Okay, over time, so we're going to assume that this booking, whether it's into the future or contains all of our bookings, both past and present, we certainly wish to allow a guest to have multiple reservations with us. Right? Otherwise, we'll probably go out of business. I certainly want, you to come back. So it's unlikely that The booking is unique on guest number. Unless we only accommodate one guest at a time, it's pretty unlikely that date from is unique, so on and so forth. Annika's sitting there like, well, maybe. If it's Roach Motel, perhaps, but we hope to run a better establishment than that. Okay, so the question becomes, is there anything that is likely to be two attributes? So can any pair uniquely identify this? Okay, so what about this one? No, why not, Tyler?
They rent 2 rooms.
Right, they could certainly rent 2 different rooms.
If they ever come back.
Or if they ever come back, right. Well, actually, we're going to, okay, I should say, I'm going to put a restriction, which is I'm not going to allow a guest to have a booking where the dates overlap. Okay, that may be an artificial one because maybe we have a wedding party and I want to book a block of rooms. But artificially, we're going to say that at any given time, we're not going to allow a guest to have more than one booking at a hotel. Okay, so that should give you, well, we can keep taking pairs. We're not going to do all of them, but we could try this, we could try the pair hotel number and room number, which was unique for room. But obviously, we may have several bookings for the same room. So it's going to turn out that no pair actually suffices here. By the way, this is showing you why you typically get a booking number, right? Because we still aren't at uniqueness yet. Okay, but given the assumption I just told you, which is that you're not allowed to have more than one booking at a certain hotel at a time, by the way, you could, if you kind of misinterpret it, assume that this could potentially be argued as a legitimate key under some assumptions. Why might this one at least be argued as a legitimate, if you, yes?
Well, if we assume you're not going to overlap dates.
If we assume that they're not going to overlap dates, and we're not going to let them overlap dates in any hotel in our chain, that could be a possible one. But I wasn't quite that strict. I said that we're just going to limit them not to have overlapping reservations at the same hotel. Kind of arbitrary, but there you go. So if I just limit them to not having more than one reservation at a time at any given hotel, then what ones become possible keys? What combinations? You can do it with a triple. Guess number, yep, so that's one. Actually not, because believe it or not, I didn't restrict them. I said they could have overlapping reservations at 2 different hotels. So maybe I put one in at the Hampton and one in at the, what is Hilton's? The Waldorf. So Hilton has a Waldorf chain. So perhaps I put in 2 overlapping reservations at the Waldorf and the Hampton, hoping to convince my wife that we'll stay at the Waldorf. But perhaps she's frugal and she's only going to allow the Hampton. So I put in a tentative reservation at both. So we're going to allow that. So it turns out, based on that, guest number, date from, and date to don't quite work. Annika. There we go. Right, so it's the first 3 will certainly work. So that gives us one candidate key. no subset of that will work based on what I've just told you. Okay, but that's not actually the only possible candidate key. Okay, so in this case, there's some other ones lurking. Yes?
Hotel number, guest number, room number?
So actually, that's a good yes, but we might actually allow, I might call in and say, I'd like to have this particular room on March 1st to March 8th, April 1st to April 8th, May 1st to May 8th. So that's probably not one that we want to enforce. Okay, although you may be on the right, well, I don't want to say on the right track, but you kind of have two out of three were right in there. Okay, go, yes.
Hotel number, guest number, and date 2.
Very good. Since we don't allow overlapping dates, it's just as legitimate to say date 2 as date from. I will grant you that that's not as intuitive as date from, but it doesn't change the fact that from a theoretical standpoint, date 2 is just as good at distinguishing a reservation as date from. Okay? There is one more that, actually there's two more that are lurking in here. I'll go with Annika.
Well, so basically you can have a whole bunch of different hotels, so that one has to be in there no matter what.
Mm-hmm.
And the guest number and the room number are going to go together. So
There you go. You have hotel number and room number. And one. Very good. So that or that. So that also gives you, as long, we don't like to double book rooms. I know the airlines enjoy double booking their seats, but we try, actually, I think hotels double book their rooms too, because I've certainly showed up and been told that, oops, and been pretty ticked off about it. So, but theoretically, we don't want to overbook a room. So there are two more candidate keys for you. So there you would choose your primary from one of those four. And actually, I didn't think too deeply about it. If I thought more deeply about it, I might find another one, but those are the four that occur to me off the top of my head. Okay. Probably, if I was choosing the primary, I'd probably go with guest number just because it's more customer friendly. So I'd probably go with those three. But this also goes to show why you typically get a booking number or confirmation number or something from a hotel, because having a, while these triplets are indeed keys, they're not very compact. The other problem is that if we're going to have to use them as foreign keys, that's a lot of data redundancy, right? That's 3 attributes that we would have to use as a foreign key. So that's not particularly good. So in general, you don't see a lot of triplets used as keys. Now, you will see some occasions where we have relations and we essentially allow the entire tuple to be the key. We'll get to that when we get to it. Okay? So, I spent this much time on it because these are great exam questions. And it's a little break from listening to me monotonically, not monotonically, but but the rest of the lecture, unfortunately, we kind of go back to hearing me talk. Okay, so we've gotten through, what have we gotten through so far? What we've gotten through, remember that last time I said a data model consists of entities, properties, relationships, and constraints. So we've certainly gotten through entities and properties right now. Those are our tables and our columns. we kind of talked a little bit about relationships in the context of foreign keys. So we've gotten 3 of the 4. The last thing we need to talk about is our constraints. And there's a number of different constraints that we may have. Okay? The first one is we actually allow a column to have a null value. It's not a value itself. It doesn't mean 0. It simply means a value that's unknown or unprovided. Sometimes we don't allow a column to have a null value. Sometimes we do. Okay, as an example of a column that may well have a null value is we might, for each time that a client goes and views a home in Dream Homes, we might create a viewing record listing the date on which the client viewed the home, the realtor who showed them the home, and we might have a field comment for any comments that the client made. We might have another field for the realtor and any comments the realtor made. It's like hot lead or, never want to see this person again. And the same thing, the client might say, well, looks like I saw a cockroach, or, I love the mountain view. So they may or may not leave comments. So those 2 fields for realtor comment and client comment would be optional. They could have null values. Doesn't mean 0 or the like. It simply means they didn't provide a comment. Now, if a field has too many nulls in it, that may indicate we need to do some kind of decomposition, which we'll talk about when we get to the design element of the course. For the time being, we won't worry about it. Okay, just to know that if something is null a lot, perhaps it should be in a different relation. You can, when you specify the DDL, you're allowed to say if it has a default value or not. So there's, you'll see when we get to it in SQL. SQL typically allows you to indicate whether the value is optional or not. So if it's optional, it means it may be null. If it's required, it may allow you to provide a default value, or it may say that it must be provided when that tuple is input. So it gives you basically 3 options. Okay. Actually, yeah, we'll stick with 3 for right now. Okay, so that is called the null constraint. The next one is called a entity integrity constraint, and it simply means that there is one column or columns that may not have a null value, and that is the column or columns representing your primary key. Okay. Why? That makes sense from what I've said. Why would it not be reasonable to allow null for a primary key? Because what? It won't be unique anymore. If 2 different tuples have null for their primary key, how can you distinguish them from each other? So the whole point of a primary key is that it's guaranteed to uniquely identify your tuple. If you allow null to be the value, you just defeated the whole point of having that column as a primary key. So you're not allowed to have null in the primary key in any column of a primary key. So that's called entity integrity. And then there's another thing related to keys. Notice that on this slide it's called integrity constraints. So they're both related to keys. So the second one is referential integrity. So if a relation has a foreign key, then it's either guaranteed to reference a primary key in another relation. And What we're saying is we do not allow dangling pointers. You know how C++ you run into dangling pointers? Referential integrity says we may not have a dangling pointer. It's illegal. If the foreign key appears in a tuple, it's guaranteed that that key appears, that particular value appears as a primary key in some other relation. So if I have, if I'm staff and my branch number is B003, there's an absolute guarantee that in the branch relation, there is a primary key with B003. If we cannot guarantee that, then we must leave the foreign key value for that tuple null. Not just one column of the foreign key, but all columns of that foreign key must be null. That's the meaning of wholly null. Okay, right here. Wholly null means that all columns of that foreign key must be null. So it's either or. Either you have it, in which case we're guaranteed that that key exists in some other relation, and if we can't guarantee it, it must be completely null. Okay, so we may have a new employee that's not yet been assigned a branch, so we give them a null value. They're not yet assigned to a branch. Maybe they're in training. And then we have general constraints. These are just constraints that are basically a constraint on some aspect of our enterprise. So we may have a constraint that no staff member has a salary that exceeds $100,000, or we have a constraint that no staff member manages more than 30 properties, or we have a constraint that no branch, that a manager may not manage more than one branch. And another constraint that says a branch has exactly one manager. Those are all enterprise constraints. Okay, there's nothing to say that we can't have co-managers of a branch, in which case we would loosen the requirement that a branch can have at most one manager. Maybe we could loosen, maybe we're going to allow someone to manage multiple branches. Then that's loosened. So it's not something that's inherent the way these constraints are. These constraints are inherent to the relational model. These aren't. These are just some constraints on our enterprise data that we wish to enforce and which we may change at our discretion. These are not constraints that we may change at our discretion. These are hard and fast constraints associated with the relational model itself, as is the null one. So 1 through 3 are inherent or intrinsic to the relational model. We have no discretion over them. They are mandated. 4 is we have discretion. We may change them, we may add additional ones, we may delete them. Okay. Yes?
The integrity, the constraints on the last page, like the one that can have a null value, those are imposed by the model though, right? They're not logical necessities.
Wait, which ones? When you said, do you mean this one or the?
The entity constraint number 2.
Number 2, this one.
Right? I mean, just for an example, like, since it's a Cartesian product, basically, you could have elements where you could have a null value and the key would still independently define.
But if the key itself had a null value, it wouldn't. If let's say that maybe we're speaking about, but let's say that the key is the first element. Okay, so if we have this situation, we don't have uniqueness, right?
Well, right. If you have that situation, I was just thinking like, just from a mathematical sense, right? Like, if you had something like the numbers 1 through 99, well, in the first 9 digits, they're null. You consider the 0 a null value, but they're independent anyway because the second value is unique.
Right, okay, so mathematically speaking, yes. But then, I see what you, but I guess the way that, I guess what I'm saying is, the way that relational model was, just like early on, we had a bunch of additional properties that were, it's the same thing here, I guess. Yeah, so mathematically not required, but these were constraints and layered on by, so yes, you're right. Okay, so that brings us to the last topic today, which is views. And remember, these are the same views that we talked about where different users have different views of the database. So they have a theoretical basis in the relational model. So we call a base relation is one whose tuples are physically stored in the database. And then we say a view is a dynamically derived relation. So it may not physically exist in the database. It may be created on the fly. So as an example, I may want a view that shows me all staff at branch B003 whose salaries are between $50,000 and $100,000. That's a view. Okay, it's not a relation that is physically stored in the database, but is derived from the base relation for a staff member. Now, all views, what's important is that, wow, I just nearly took this pen and put it on the smart board. Came very close. Okay, so all views are relations themselves. So this is really important. Every view is itself a relation. So every query that we write is going to itself result in a relation. That's why I said earlier, when I was saying that a relation can be specified mathematically, that's what's happening with a view. It's a mathematical specification of a relation. Now, we use syntactic sugar so that it seems like a natural English-like description of the view, but in fact, at its heart, it's a strict mathematical specification of the relation. So we say that the operations on a relation are closed because any operation on a relation itself yields a relation. Okay, and alternative names for a view are a derived relation or a virtual relation. And they are created from a query on one or more base relations. So it doesn't have to be derived from a single base relation. Okay, I could say, give me a view that lists the names and, let's see, what do I want? Yeah, give me the names and salaries of all staff who work at 163 Main Street. Now, in order to create this view, I'm going to have to look at both the branch relation, let's see if I have it here, there we go, and the staff relation, because from 163 Main Street, I can get that the branch number is B003, and then using B003, I can find the salaries of all staff who make between 50 and 100,000. I see that we're cheap. Good. We keep a lid on our costs. So don't want to work for me, I guess. Of course, these are in pounds, you must remember, although the pound isn't as strong these days. Okay. At any rate, that query I just gave you, or that view, which is list all staff at 163 Main Street who make between 50 and 100,000, that view is derived from two different base relations, the branch and the staff. Okay, so as I said, it's not necessarily existing in the database, although often it's cached. So for performance purposes, we will often cache views, especially commonly requested views. But that's an optimization or implementation issue. It's not strictly part of the relational model. Okay, as I said, it's defined as a query on one or more base relations. They're dynamic, meaning that when a change is made to the base relation, it should immediately affect the view. If the view in any way is affected by the change, then that change should be immediately propagated through to the view. Which means if it's cached, we have to invalidate the cache and reperform the query. Remember last time we talked about logical independence, and the whole point with logical independence was that if a base relation changed, but it did not affect some view, then that view should not have to be recomputed. That was logical independence, and the beauty of logical independence is it allows us to do caching. Hey, and we've already talked about probably one of the most important points of views is it provides a very powerful security mechanism because it hides sensitive parts of the database from certain users. Okay, but even if a user is allowed to see certain data, sometimes they want to see it in customized ways. Often they want to see it in aggregated ways. So I might want to see for CS465 the number of A's, the number of B's, the number of C's, the number of D's, and the number of F's. So I have access to the grade field, but I don't want to have to sit there and count manually the number of A's, the number of B's. What I want is a customized view that's going to give me 5 tuples. One that is the number of A's, one that's the number of B's, one that's the number of C's, and so on. So views give us a way of customizing, often aggregating data. Okay, especially managers typically want to see, actually most people want to see aggregated data, to be blunt. And finally, you'll find out as you get into some of the homework assignments, they can be used to simplify complex operations on base relations. Just like you use temporary variables sometimes to simplify a computation, right? It's a long computation, so you store part of the result in a temporary variable, and then you use the temporary variable in a future calculation, and it simplifies it. That's what a view can do. A view can be used in effect like a temporary variable, so that you produce a relation which then can be further used in another query, but it will be a simpler query then. So instead of doing one complicated query, you might do 2 simpler queries with the relation produced by the first query being used as input to the second query. So that's what 3 is. Essentially think of it as a temporary variable in that case. Okay, and finally, we talk about updating of views. So a couple requirements. Obviously, all updates to a base relation is immediately reflected in all views. That was already stated back here. And then if a view is updated, then the underlying base relation should reflect the change. So if we have some view that shows all, let's say we decided that we're going to give anyone under, say, $60,000 a raise to $60,000 at Dream Homes. So we might at branch B003. So we might have a view, and it says, okay, here's all the people who make less than $60,000 at Dream Home, and now, not at Dream Home, at branch B003. And I now update all the employees in that view so that they have a salary of $60,000. That means the underlying base relation should also immediately be updated. Obviously, it does no good to update the view and say, congratulations, Annika, we're now giving you $60,000. You're happy, you go home. This is great. End of the month. Oops, still making that same miserly 30,000 pounds that Dr. Van der Zanden paid me. What happened? The change didn't go through to the base relation. Annika quits in a huff, puts on social media that Dr. Van der Zanden is a tightwad who lies, and lawsuits ensue, blah, blah, blah. Okay. But because the updates go through to the base relations, there are some restrictions, and we'll get into these more in the future, but the big one is that the updates are allowed only if the query involves a single base relation, so it can't involve two base relations. If my view had said that I want all employees who make less than $60,000 at 163 Main Street, I can't update the view anymore because now that's a query on two relations, the branch and the staff. As an example of why you probably don't want to allow updates when it's multiple base relations, think about if we have a client in our database and they've leased multiple properties from us. And we also have a lease relation. Well, and what we get is we have a view that shows the current, a single tuple that shows the current lease for this client. Okay, so maybe we have client number, we have lease number, some information like the current monthly rent, which I'll abbreviate MR, the start date, the final date. Maybe we have, say, the customer name. So this is a combination of information from two different, thought we'd fix this problem, but I guess we haven't. Combination of information from two different relations. And now I say, okay, we're going to delete this particular tuple. Well, how do we exactly map that back to the base relations? Do we really want to delete that client from the database? Presumably, we don't want to delete all the leases that this client has held in the past. So that's the problem, is that if you have combined the view from multiple relations, base relations, it may be fine to delete this single lease from the lease relation. That's not an issue. But if we have to do some deletion from the client database, the only logical thing is that we delete the client. But there's other leases associated with that client. That's bad. So that's why we have the restriction that if the view was formed from multiple base relations, we can't update it because we can't easily map it back to the individual base relations. Whereas if there's a single base relation, it should be pretty clear. Okay? Second, the updates are not allowed. I'm sorry. Actually, that was B. The first one makes sense too. The updates allowed only if the view contains a candidate key. If it doesn't, let's say that the view is one that doesn't have one of its fields is date of birth. And maybe another one is position. Okay, so position, and we decide we're specifically going to delete this tuple, just this one that has like manager and 2, 10, 80. Well, it may be by pure dumb luck that there's 2 managers both born on February 10th, 1980. Without the candidate key, we don't know which one to delete. So we have to have a candidate key. Notice it's not a primary key. It's a candidate key, because a candidate key, if you remember, uniquely identifies a tuple. So it's enough for us to have the candidate key. And then the final thing is that we don't allow an update if the views columns were formed from aggregation or grouping operations. So for example, let's say that I'm looking at my grades for CS 465, and my department head just told me, gosh, Brad, you are Santa Claus. It looks like you have 50 A's here and only 5 B's and no C's. Unacceptable. We have standards. Okay? So you're going to only assign 30 A's, and you're going to assign 10 B's, and you're going to assign 15 C's. Okay? So does it really make sense for me to go in and change my view so it now has 30 A's, 10 B's, and 15 C's? How are we going to map that back to the base relation? Which 20 people no longer have an A? Okay? Which of them get B's and which of them get C's? See, there's no easy way to map it back. I can change the aggregated field, but that doesn't allow me to map that update back into the base relation. We all agree with that? So that's why those 3 restrictions exist. Okay, so that's our introduction to the relational model. Next Tuesday and Thursday, we're going to head into Chapter 6, so temporarily skip Chapter 5. We'll talk about actual operations we use to retrieve and update information on a relation.